start with my introduction now, which is of course less important than the presentations that we are going to hear. So the people that are joining are not going to miss much. When in spring this year, Victoria approached me with the idea to organize a special session for this conference. I was first a bit reluctant, but she was very active and convinced me that this was a very good opportunity and good idea. And seeing this conference and the talk so far, I think she has a really good point, and it's a pleasure to present here and to be here at this conference and to see the many people here with the talks that match a lot of the research that we see and that are very relevant to us. Especially here we are in this context of dynamic optimization, which means we having very practical problems in very short time to solve and to make decisions. And of course, this is a challenging task from many points of view, the time required and the complexity of the problems involved. And this requires some new methods. And so I think we have a good setup here. We have 3 talks. I want to welcome Stefan Wagner with his talk on the Josef Ressel Center adaptOp, Adaptive Optimization in Dynamic Environments, which is a big project that we have acquired and that he's currently leading at the FH Österreich in Hagenberg. Then we have a talk from Karl Schneeberger, who is employed at the Industrie-Logistik-Linz GmbH about steel logistics, digitalization of dynamic problems. And we have a talk from Gerald Fehringer, who is employed at LISEC Austria GmbH, with his talk Challenges and Solutions for Optimization in the Glass Producing Industry. So very practical talks from the industry, and I think without further words, I want to give Stefan the opportunity to present the research project and to tell us something about adaptive optimization.
Yeah, thank you, Andreas, for the introduction. You should by now see the screen that I'm sharing, and I'm very happy to have the opportunity to introduce you to our Josef Ressel Center adaptOp, which stands for Adaptive Optimization in Dynamic Environments. In fact, if we listen to the talks that we were able to hear in this conference, I think it gets clear that dynamicity is a challenge in production and logistics. So we identified also this challenge in our research project here, and that's why we especially focus on how we can solve optimization problems in production and in logistics, which have dynamic elements inside them which change over time. And this is in fact in its core our main research topic and challenge in our Josef Ressel Center. It's a pleasure for me to start this series of 3 talks. And in fact, the 2 upcoming talks by Karl Schneeberger and Gerald Fehringer are 2 talks of our company partners in the Josef Ressel Center adaptOp. So you will also hear the perspective of our company partners and their challenges and their solutions that they face in their daily work and in their daily optimization problems that they have to solve. But it's a pleasure for me to be able to start with the general introduction of our Josef Ressel Center first. So my name is Stefan Wagner. I'm professor at the campus Hagenberg of the University of Applied Sciences Upper Austria, and I'm also head of this Josef Ressel Center. I want to start with a very brief introduction with our research group. So we are the research group for heuristic and evolutionary algorithms. And you might note Michael Affenzeller just in the middle, in the front row, who is the head of our research group and also one of the main organizers of this ISM conference. So in the meantime, we have been quite growing. So we started our work at the campus Hagenberg in 2005, and we are working on solving operations research optimization problems since that time. And in fact, we were able to gain several larger research projects in this area, and we started with the first Josef Ressel Center that was there in Austria from 2008 to 2013, which was named the Josef Ressel Center Heureka. And then we had a follow-up project from 2014 to 2018, which was a K project in the COMET research program of Austria, which was named Heuristic Optimization in Production and Logistics. And we also have another Josef Ressel Center currently led by Professor Gabriel Kronberger, which is the Josef Ressel Center for Symbolic Regression. And last but not least, our Josef Ressel Center for Adaptive Optimization and Dynamic Environments. And I show you this slide to give you the impression how we came to the motivation to apply for this new Josef Ressel Center and what we wanted to solve with this Josef Ressel Center. Because we focus on applying meter heuristics and applying optimization algorithms to production logistics problems since 2005. So already in the Josef Ressel Center Heureka, we applied meter heuristics to solve production scheduling problems, for example, or to solve layout planning and flow optimization problems. In the heuristic optimization production and logistics project HOPL, we especially focused on different production and logistics processes which depend on each other, and we investigated how we can solve different processes, production and logistics processes together, so that you do not strive for a single optimal solution for one isolated process, which might be not optimal for the whole system, but how to balance the optimization of different dependent processes so that the overall solution for the whole production logistics system gets optimal. And based on this foundation of these previous works, we identified that dynamics in production logistics processes are really of major importance. And that was also the motivation and the basis for applying for the Josef Ressel Center adaptOp. And I want to just give you an impression of exemplary production process from one of our company partners. This is voestalpine, a steel mill located in Linz. And here we have a look at the steel production process from casting, so from the steel slabs that are produced here to rolling. And you see on the picture on the left-hand side, you see the hot steel slabs coming from the continuous caster, and then they are stacked. So there is a crane which has to pick up the slabs from the end of the caster and has to put these slabs aside. They're still very, very hot and have to cool down, partly to be able to transport them the further way through the production system. So we have a stacking problem to be solved here, because the space available for stacking the slabs is limited, and you do not want to put slabs on top of each other where you need the lower slab immediately before you can transport the upper slab again, because then the crane would have much work to do to reorder the slabs all the time. So here we have a stacking problem. And after the stacking problem comes transportation of the steel slabs to the rolling mill. And it can be that the slabs are transported if they are still hot, but it can also be that the slabs are transported to a storage area. There are large storage areas where the slabs are parked until they are further processed to the rolling mill. And it can also happen that some post-processing is necessary. For example, if quality control notices that there are some defects on the slab after casting, then it is necessary to post-process the slab before it can be transported to the rolling mill. And of course, there's also the way in between from the storage area to post-processing and then to the rolling mill. So a lot of different ways how the slabs are transported through this production system. And of course, there are also several different vehicles to do the transportation. You see a straddle carrier on the left-hand side, and a truck and trailer on the right-hand side, and a vehicle, a so-called reach stacker, which can grab a single slab in the middle. So this is the situation that we observe. And of course, there are a lot of dynamic effects which also take place in this production system, and then which affect the slabs on their way from casting to rolling. And one of these effects, as I mentioned before, is, for example, quality control. So if we have a look at the stacking problem that we solve at the end of the continuous caster, then we have an event. The event is, okay, now the slab is casted. And if the slab is casted, we have to solve an optimization problem here. We have to decide where we should put this slab from the caster to one of the stacks located near the caster. So how do we solve this optimization problem? We have to take the data from the production system, we have to transform this data into a formal problem definition, into an optimization problem, and then we can apply one of the optimization algorithms that we use. That could be meter heuristics, this could be exact solvers, whatever. So we apply some form of optimization algorithm to get an optimal solution for this stacking problem, and then we transfer this data back to the optimization, back to the production system to provide a crane assignment. So the crane assignment would then tell the crane, okay, pick up this slab from the caster and put it on stack X or stack Y or whatsoever, and this results in a crane motion. So in fact, this way of thinking about problems and solving problems is what we do in fact, since 2005, with various different algorithms that we apply and different problem models that we apply, and so on. And now we have dynamics. Dynamics occur because after the slab is casted, quality control comes into play, and quality control checks if the slab is okay or if there is some post-processing necessary. And it might be a result of quality control, of course, that some post-processing is required. But we do not know this information that post-processing is required just at the time when the slab is casted. So quality control takes some time. And so we usually immediately start with our optimization algorithm. And as the optimization algorithm is executed, it might happen that this result from quality control comes back, which tells us, okay, we need to schedule post-processing for the slab. And this means that the target stack that this slab should be put on is a different one as we expect now during our optimization, because the time when the slab will be transported further on in the production system will be a different one, because this post-processing step has occurred and has to be planned into the production steps of this single slab. So what happens in that case is that we computed a very nice solution, hopefully a very good solution, maybe also even an optimal solution, but after optimization we can throw away the solution because things have changed. And this new information, the quality control requires post-processing of the slab, just emerged during our optimization algorithm, and so we have to either redo the work, so we have to restart the optimization algorithm again, or we have to think about how we can incorporate such dynamic changes into the optimization algorithm during its runtime. Of course, restarting optimization is trivial, but leads to several problems. One of the problems is that you would have to make optimization time very short if you want to restart the optimization again and again after each change that occurred, which limits you in the quality that you can get. Roughly, we still can say that having more time for executing the optimization algorithm will lead to better results. So we want to have long time to compute the result. So this is a problem if you have to restart the optimization algorithm all the time. So integrating these dynamic effects is the better idea. And this idea is what we strive for in our Josef Ressel Center adaptOp. So what we want to have, and the vision that we follow, is we want to have an adaptive optimization system. So in fact, we have a dynamic production process which just flows over time, and parallel to this dynamic production process, I want to have an adaptive optimization system. So I do not want to start an optimization algorithm each time when a specific event occurs in our production scenario, but I want to start it once, pass all the data that is relevant for the adaptive optimization system at the beginning, and then I want to have a continuous communication between the dynamic production process and our optimization system. So there are change events that occur that the production system has to communicate to our adaptive optimization system, and on the other hand, the adaptive optimization system has to provide actions or has to recommend actions to the dynamic production process so that these actions can be followed in the production process itself. So that's the vision where we want to get to. What do we need for such an adaptive optimization system? First of all, we need to take this dynamic effects in our problem models into account. So we need dynamic problem models, and we need optimization algorithms which can react on dynamic changes as they occur during their optimization. And this is a challenge because each heuristic search, for example, that you can use to solve such a dynamic problem assumes that the solution space and the quality landscape of the optimization problem has a specific shape, and regarding this shape, it optimizes its search trajectory to better solutions. And if this shape of our solution landscape, of our quality landscape changes, we have to build in mechanisms in our algorithms to be able to react on that so that we can restart optimization at specific points, for example, or that we maintain enough diversity in our search process so that even when dynamic changes occur, our optimization algorithms will be able to find promising solutions in acceptable time. So the first part is reactive optimization and dynamic problem models, where we put the focus of our research on. Then the next aspect is that we want to learn. We see that this adaptive optimization system observes changes which occur in the dynamic production process and provides recommended actions. And we want to observe these changes, and when we want to learn from these changes. So we have to integrate machine learning so that we can build a model which helps us to predict future events. And we want to predict change events which happen in the production process on the one hand, and on the other hand, we also want to predict the potential performance of our optimization strategies that we have. And that's quite interesting, so just keep a second to think about these two aspects. I think it's quite clear that we want to build machine learning models which predict these changes that occur, which will give us the possibility to predict future scenarios, and so that the optimization can prepare for different scenarios that might happen in the future, so that if some of these changes then really occurs in the real world, the optimization can say, okay, well, I've foreseen that. I've already computed a solution which takes this change into account, and that's my recommendation what you should do. That's, I think it's quite clear. It's not easy to do, but the vision is quite clear. On the other hand, due to these changes and due to the constant change of the landscape of our optimization problem and of the qualities of our optimization problem, we might also have to switch between different optimization strategies. So there are, for example, optimization algorithms which focus on a more diversifying search, or ones which focus on a more intensifying search. And depending on the characteristics of the optimization problem that we have to solve, we have to take one of these algorithms which are well suited at the current situation to solve the optimization problem at hand. And this might change over time due to the dynamic nature of our optimization problem. So we have to use machine learning, on the other hand, to predict the performance of our optimizers that we have, so that we can choose the right optimizer at the right time, which is suitable to solve the optimization problem with its current characteristic at a specific point in time. So that's why integration of machine learning is of such a major importance here in building such adaptive optimization systems. And if we integrate these two, so the dynamic problem models, the reactive algorithms, and the machine learning models to predict these events and optimize the performance, we will be able to build adaptive optimization algorithms. So optimization algorithms which reconfigure themselves, which change their parameterization, for example, depending on the current situation, the production process is in, the production system is in, and that's the goal which we strive for in our Josef Ressel Center adaptOp. So just to sum up, to summarize the research program that we have, so we started with modeling of dynamic problems. In fact, we started with this Josef Ressel Center roughly 1 year ago in October 2019. So we have the first year completed now. We have hopefully 4 more years to go. So there's still a lot of work in front of us. But in the past year, we started modeling dynamic problems to identify relevant changes in the production systems of our company partners involved in this Josef Ressel Center, and we included this dynamic effects in our problem models in order to develop reactive optimization algorithms. So this is the first stage of our research program. So we want to have optimization algorithms which are applied multiple times, because we have to solve these optimization problems again and again. The stacking problem, for example, if we have a look at the steel slabs after casting, the stacking problem has to be solved each time when a new slab comes out of the caster. So we have to solve these optimization problems again and again, and we want to benefit from repeatedly solving the same problem, and we want to reuse data that we have from a previous optimization, for example, and the follow-up optimizations. Therefore, we can react on changes that occur. So this is the first stage. Second stage would be to integrate machine learning to go from reactive optimization, which observes and notices changes and reacts to changes, to proactive optimization, because we can observe the change events and we can use machine learning to build prediction models all the time when the adaptive optimization system runs parallel to the real production system. We want to predict changes, and we want to prepare for these different scenarios which might occur in the future, because we know to which probability such change events might occur due to this learning that takes place. And stage number 3 is to combine these two to adaptive optimization algorithms, which continually adapt to emerging changes, adapt by changing their configuration, for example, or also adapt by changing the optimization strategy as a whole, so that we can provide optimal action recommendations all the time, even though that changes in the production system affect how our optimization problem looks like. So to give you an overview of the center itself, we have 4 company partners. 2 of those are going to present just right after me. So one is first up Industrie-Logistik-Linz GmbH. One of the presenters, Karl Schneeberger, which will also continue after my talk, is from Industrie-Logistik-Linz. There we focus on stacking and storage of steel sheets and coils. We have the logistic service company, also located in Linz, in our team, and Mr. Gerald Fehringer, who is the third speaker in this session, is from LISEC, Austria, and they are producing flat glass production machines, and there we focus on scheduling the production orders in such a system of flat glass production machines. But I leave these the details on these 2 applications to the speakers, which will continue right after my talk. Just to give you an idea what we achieved so far, I want to show you a picture of the system architecture that we came up with to be able to build such an adaptive optimization system. And so we usually have some form of production information systems that provide us some data continuously on the production system that we try to optimize. And as we want to have a continuous open-ended adaptive optimization, which is not started when an event occurred and then provides a result, but which is continuously and asynchronously executed in parallel to the production information system, we have to decouple these two processes. So the production process and its information system on the one hand, and the optimizer on the other hand. And we do that by putting a message queue in between. So the production information system pushes messages each time when such a change event occurs, each time a new data in the production system is available. We pass this data to the message queue, and the message queue stores all this information, and the optimizers are attached to this message queue and are able to retrieve this data, these messages, and are also able to send messages on their own to the message queue. So communication between the production system and the optimizers is decoupled using a message queue. And in our case, we have implemented a reference architecture for the system already. We use 0MQ, for example, or ActiveMQ as message queues for that purpose. And then you see that we have optimizers. It might be several optimizers. There's not a single optimizer, but different optimizers, because they, for example, can also explore different scenarios. So one optimizer computes a solution for a specific scenario, and another optimizer computes another scenario if some changes might occur in the future, for example. So we have different optimizers. We use our own optimization system heuristic lab here. We also use branch and bound algorithms or commercial solvers such as Cplex or Gorovi or whatever. And we use these optimizers to solve one specific problem model. So you see that the problem model that the optimizer requires for solving the optimization problem is integrated into the optimizer. We use simulation models for that purpose. So we have a known discrete event-oriented simulation framework called SimSharp, developed by Andreas Beham, who chairs this session. Or we also use MIP models or constraint programming methods, or also heuristic methods to represent these models. And so the optimizer interacts with the production system and provides new solutions, provides action recommendations just on time. And this will be the mere reactive optimization side. Something happens, the production system informs the optimizers by pushing messages to the message queue. The optimizers retrieve these messages and react on these messages in some form. And now we have to span we have to think about how to integrate machine learning and how to integrate this prediction into the system architecture. And so we have another possibility to attach a simulation system to the message queue. This is what we need to drive different test scenarios. So we are not only working with the live production systems, of course, we have also developed simulation models of the whole production system of our company partners that we are looking at. And we use the simulation models for testing our architecture. And then we can attach learners. So the message queue, the events that occur in the message queue contain information about different change events, and the learners listen on this message queue to retrieve information on these change events and to process these events somehow. And you see that we have a different variety of machine learning methods that we plan to apply here, starting from very simple ones such as linear regression to very powerful machine learning methods such as symbolic regression, Bayesian networks, or artificial neural networks, or whatever. And the learners push information about these different events to a time series database. In our case, we use InfluxDB in that context. So we have a time series database where we can protocol all the different change events that occur, and we can also predict future change events also on this time scale that the time series database provides. That's why we have two-headed arrows here from the learner to the time series database, because they push the observed events to the time series database, but they also retrieve the historical events and try to build models to predict future change events by the purpose. And so we can use this time series database to hold historical data, but also to hold predictive data for the future. And then the problem models can retrieve this data from the time series databases to update their scenarios and to update their problem model accordingly. So this is the overall picture of the system architecture that we are following in our Josef Ressel Center and some of the first results of our project. And as I said before, we have also already implemented the system architecture for benchmarking purposes. So one big problem in dynamic optimization problems is the lack of meaningful benchmarks. And by meaningful, I mean benchmarks that are complicated enough to be real benchmarks for real-world applications of dynamic problems, because of course there are benchmarks such as the moving peaks benchmark or whatever, but they are very, very simple, and we all know that real-world production systems are much more complicated. So benchmarking is really an issue, and we decided to create a web application for benchmarking solvers, in that context for dynamic stacking. The simulation is run on a server which we host in real time, and solvers can communicate with the simulation to provide optimized crane moves. And we have different training scenarios and different evaluation scenarios. And we implemented this benchmarking infrastructure also to provide a common platform for benchmarking dynamic optimization problems to the community. And that's why we used this benchmarking infrastructure for a competition at last year's GECO. In fact, at this year's GECO, so GECO 2020, and we made a competition on dynamic stacking, and we also submitted it to GECO 21, which will be next year. I hope we get accepted with this competition once more, and if you're interested in developing solvers for such a dynamic crane operation and stacking problem, I invite you to have a look at the GECO Competitions 21, and if you are accepted, to participate in our competition also next year again. So as time now is running short, I think I have to come to an end. So what are first results and what are next steps that we are going to focus on in our Josef Ressel Center? Just to pick a few of the results, we have reviewed dynamic problem formulations, of course, in production logistics. You have maybe heard these results in the talk of Victoria Hauder, who gave her talk yesterday. And we created the system architecture and software infrastructure that I presented to you 2 slides before. And now, of course, we are working on dynamic problem models for transport and crane operations and scheduling. This work is done together with the University of Vienna. The University of Vienna is the second scientific partner in our Josef Ressel Center. And they especially concentrate on dynamic problem models for transport problems, and we concentrate on crane operations and scheduling. And we evaluated different heuristic rules and different solvers to get an analysis of the impact of dynamic effects on solver performance. And maybe I also want to mention that one of our colleagues in the Josef Ressel Center also implemented a new solver for solving block relocation problems, which are the stacking problems based on the new relaxed version of the BRP, which provides much better lower bounds than existing solutions. So these are results from the first year of our Josef Ressel Center, and now in the next steps we are just on the border of going into this integration of machine learning. So we want to analyze the impact of dynamic effects on the fitness landscape. So how do the optimization problems change when dynamic effects occur? How can we implement the system architecture, this integration of machine learning, and how can we automatically adapt our problem models and adapt our algorithms, selection of algorithms and configuration of algorithms, so that we can react on and deal with these dynamic effects on the fitness landscape in our optimization problems. So this was a short overview of our Josef Ressel Center, and I'm very happy that we now get more detailed insights into the application scenarios and into the production systems of our 2 company partners, ELL and LISEC Austria. And yeah, that was my talk. If there are any questions, feel free to ask. Thank you for your attention.
Thank you very much, Stefan, for this interesting talk. I want to apply to the audience. If you have a question, please use the raise hand feature. We have time for a quick question. We're a little bit over time, but nonetheless, if you have a question, please raise your hand. Or if you cannot raise your hand for some reason, then please just unmute yourself and ask the question. Meanwhile, while Karl is preparing his talk, Stefan, what do you think? I mean, this is a very ambitious program also. What would you say is one of the big challenges that we have to overcome in the next few years? What would you think is the biggest obstacle to successful application?
Well, I think the biggest obstacle is still handling all the data. I think we have good methods for optimization. We have good methods for machine learning, but in fact, are these methods really fit enough to deal with all the obstacles that we have in a real-world application would be the major challenge from my point of view. Yeah, because it's easy to get a lot of data out of these production systems, but you do not need just a lot of data. You need the right data to be able to feed it into machine learning models and to deal with data and to extract the relevant information that you need. And automating this process of data processing and data preparation is something which is also targeted in the research community regarding automatic machine learning, for example. But I feel that we are still on a very interesting phase of research in that case, so that we really have to try how to apply these models and these ideas that in the research community are coming up now to production scenarios which are as complicated as they are in the real world. So this will be maybe my answer to this question.
Yeah, thank you very much for this insight. I agree to a lot of to a big extent to this. I see this very similar. Okay, so without further ado, there is the next talk given by Karl Schneeberger. Please, Karl, the stage is yours.
Thanks for the introduction. So at the first, presenting to you the steel logistics digitalization of dynamic problems. I mainly focus on one of our biggest warehouse of steel coils. So before that, maybe the Industrie-Logistik-Linz is a logistics provider. It also provides some logistics know-how to the voestalpine. So we are located at the voestalpine plant directly here in Linz. And this is one of the biggest warehouses the high performance warehouse INAL. So here are some facts and some pictures of this amazing and big hall warehouse in Linz. Which goods we are handling here? It's mainly steel coils. As we saw before, there were some slabs. The slabs are getting rolled. That was the rolling mill and some other treatments. After that, it's a kilometer long a stripe that is wrapped up to a coil. We can see it here in more detail. I zoom it in to show you that. This is a steel coil with up to 32 tons. So they are really huge inside and even are hard to handle. So the dimensions of our warehouse is about the length of 400 meters and also the width of 40 meters. So we get enough space to store coils in here. We are operating the in the warehouse with 2 cranes. They have some magnets. We can see it on the left picture with the yellow magnet. There, the coil, the magnet is positioned on the top of the coil. The magnet is magnified, and then we can move the coils from one to another position. Maybe some interesting figures. We have up to 18,000 tons available in this warehouse. So this is about 5,000 coils. So this is also the challenge we have to handle here in that. Maybe some figures about the outbound process. We have at the high times up to 5,500 up to 6,000 tons. There's about 300 to 400 coils we are dispatching all day long. For this specific day I picked out, there were 18 trucks loaded with 60 wagons, and also some intra-warehouse or intra-plant transfers with trailers. There are specific trailers that are able to load weights with up to 100 to 200 tons. They are used to transfer the goods within the several warehouses we are operating here in Linz. So at this talk, I only focus on this specific hall. We can see at the bottom a figure about that. So we have 2 cranes, one in the north and one in the south. The cranes cannot cross, so if the violet crane is moving to the south, the orange one has also to move to the south. And we have a warehouse management system that is programmed mainly by our programmers. So the development is in-house. It is also necessary to operate these cranes because, as I mentioned before, we have up to 5,000 coils in the warehouse. So we need some digital information about the situation or the location of the coils. To our loading equipment, we have 2 train tracks indoor. So it's called the track 228 and 229. At the largest train track, we have space for over 30 wagons, and at the smaller one, up to 10 wagons. So at high times, we are able to load these 30 wagons with about 100 coils within 8 hours. So this is some of the things we do in this warehouse. In addition, we have also 6 indoor truck slots. They can be indoor at the same time. They are in the south. This is the green area at the bottom of the picture. It's called EKW area, so it's for the trucks. There, the trucks unzip their cover, and after that we are able to load that. We also, as I mentioned before, had some trailers for the inter-warehouse transactions. So if we have to load a coil in another warehouse, or if some quality issues appeared, we can bring it back to the plant. In addition, we also got 10 shuttle slots. They are directly connected to our production plant, and so we are able to minimize the trailer transactions between the warehouses. Otherwise, we have, as I mentioned before, we get up to 5,000 tons of loads each day. So we also got import into the warehouse from up to 2,400 up to 3,000 tons. So we need a huge amount of ingoing coils. What is our objective? We want to fully automate the complete warehouse. it is not that easy to automate such a warehouse because of the fact that there are many people interacting in this warehouse. For example, at the track slots 1 to 6 at the left hand side here, we got the problem that there are truck drivers. We also have workers that are doing some preparation at the trucks or to check the loadings and so on. So there are many people in the warehouse. So we divided the warehouse in two areas. One is within the automatic area. It's within the red line. There we can do all our stock interchanges and also the ingoing process from the shuttles. All other operations to load vehicles only can be done by a crane operator. Our idea is that the crane operator is now still operating at a crane cabin in the top of the crane. We want to move, as shown in the picture, the crane operator into the office, and therefore he would be able to operate more than one crane at the same time. Therefore, we want to automate the crane that way that they are moving several coils, as example in the north of this figure here. You can see that of this picture here, you can see that the crane is probably moving to the north and is waiting for the crane operator. The crane operator, when he has some lack of time, or some time left, he switched to the crane, and then the crane will load the vehicle. So only under a supervisory the crane is able to leave the automatic area. So what we need to know each vehicle position. We need also to fully automate the cranes, and the real challenge is to give the cranes the direct orders or the correct orders to get a smooth flow in the warehouse. Another challenge is that the crane operator is not longer anymore operating in the crane cabin at the crane itself. So we have to move it into the office. Therefore, there are some legal, from the legislation, some restrictions we have to handle to be able to do that. So that's not that easy, and is also in kind of restricted to do no violation to people. So what are our digitalization challenges? We have to do some production forecasts to know in which time we have some incoming calls to the shuttles. We also have to do that for the internal trailers because they are dynamic. They can appear at each time. So we have to do some forecasts that we are not interrupted in the loading process over the time. We also need to know the positions of each vehicle, especially for the trucks, because there are normally only 15 minutes within our warehouse. So they are leaving really continuous over the day. And therefore, we have to load a truck within 15 minutes. The same for the wagons. We also have to know exactly where the 30 wagons are in the warehouse, and also the other 10 wagons at the track 229. So if we don't know that information, we cannot give the crane a correct advice where to go, and we have to manipulate through a crane operator, a manual one. Another challenge is here the wagon cover identification. So as shown at the picture on the left. So normally they have to we have to open the wagon cover, and if it's opened, we only are able to load some of the coils. So at this example, we can load 5 coils in the wagon. We have the problem that if the wagon cover is in the middle positioned, then we are only able to load coil 1 and 5, and only through a movement of the wagon cover by man, we are able to load the other ones. So this is also one of the points we have to consider to correctly advise the crane what to do at the right time. One of the helpful hints is here that we are not allowed to move these wagon covers by crane because they are maybe damaged, and then it's not possible to use the wagon anymore, and it has to be repaired. Another one is the trailers. Also, we have to unload and load up to 10 coils each 2 hours. Therefore, there are in these 2 hours up to 3 trailers within the warehouse. Therefore, we also need to know where they are positioned, when they arrived, when we have to unload all these coils. The same is for the shuttle, but here we have not the problem of a lack of information. They are already in our system, so we exactly know when a shuttle arrives, and also what is positioned or which coil is available at each time. We also need to know some dispatching information, so which product has to be loaded on which vehicle, and the time range of loading. So we need to know when the coil is, when it's possible to load the coil on the vehicle, and also when we have to do the loading. So we don't have that time to say that a vehicle is too long in our warehouse. Another one is also the identification and the verification of all coils are on a vehicle. So we also do a photo documentation. It's done by our workers in the warehouse. This is due to quality issues and also of the securing of the loads. So we have to secure the lashes on the vehicles that the coil isn't able to move while it's transported. We also have to do, as I mentioned before, some intra and inter-warehouse stock transfers. This is due to quality aspects, or also what we have to do is to do some intra-stock exchange, because as example here, if we want to remove or want to load the coil at the position C9, we have to remove one of the coils from the second layer to be able to load this coil. So therefore we have to do some stock transfers, and to do that we have also to look at some quality aspects. For example, we are for some coils not allowed to move it in the second row, or it's not allowed to be that another coil is stored at the top of this coil. At the moment, we have lots of information for the crane operator. There are some transport tasks or loading tasks that he has to do. For example, at the 30 wagons, there it's possible that the crane operator gets up to 120 coils to transfer to this or to load at these wagons. Therefore, there's a huge amount of information that the crane operator has to handle. What are our digitalization strategies to achieve automation in this warehouse? Therefore, we have the Josef Ressel Zentrum, as mentioned before, from Stefan Wagner. We want to automatically assign our transport tasks to each crane, and also want only to visualize one of these tasks. So we want to give the crane operator no more the opportunity to do something else like the system says him to do. So we have to optimize the crane flows, and we have to consider some relevant constraints. One of the constraints that is the hardest to consider is that the cranes cannot cross each other. So we are not able to, the crane, as I mentioned at the beginning of the presentation, that the south crane cannot move to the north with crossing the crane from the north. So we are not able to do such moving. So we have to consider that the other crane has to also go to the north and to give the south crane the possibility to do its transport task. We also have to do some intra-warehouse stock transfers due to the fact that we want, as I mentioned before, if we want to handle or to load the green coil at the position C11, we have to do some rearrangement of the other coils here considered as a blue coil. We also give each coil a time window, a start and an end. So it's we need to know when it's ready to load and when it should be done. This is also necessary to give the system some input how and when to do the loading process, and also to give the system the opportunity to do some stock transfers. In the best case, we do the stock transfers before the loading, so we have a better or continuous utilization of the cranes. At least we have to have one free shuttle slot because of some issues if the plant has to deliver more coils. So we don't want to stop the production plant. We also get many dynamic problems. So we have some crane defects, we have incoming vehicles, we have incoming coils from the shuttles, we have incoming coils from other warehouses. So we have these challenges that we are very dynamic and have to handle lots of problems within a few hours or minutes. Here is the crane operating problem visualized. So we don't want the cranes to move in different directions as shown in the upper picture. We want them to do directions in the same, do some movements in the same directions. So it is better to pick up the coils in the same directions and do such movements, so that there is no possibility that the cranes cross and has to wait. Yeah, we want to digitalize our vehicle positions step by step. So for truck and trailers, in the first step, we're using a scanner, as shown in the picture before. Maybe flash here at our Zebra. So we got several scanners. With these scanners, we want to do some assignment of trucks and trailers to some specific slots. We also can say when the start of the loading should begin and the estimated loading time. And also we do the full photo documentation with the scanners, with the photo documentation tools we already have. In a second step, we want to use some 3D scanners and also cameras. It's kind of necessary to get some registration of the license number of each truck and trailer, so we know which products are necessary to be loaded on these vehicles, and also some scanning tools to know the exact position of this truck. We also have some scannings to know if the truck is covered or not. So if it's uncovered, we are able to load the truck, and if it's covered, we are not able to load. So we have here the possibility to do some automation in the recognition of vehicles. Because of some predictions, we can also estimate the loading time and can therefore guarantee that the loadings of each trucks that are incoming the next hours are able to be loaded. Also, one of the interesting points would be here to automatically do the photo documentations with some cameras in the top of the crane. So maybe we are able to replace the scanner totally. Another digitalization project of our vehicle positions would be the wagons and on the tracks. So at the first, we know the numbering of each track. So we know at position 1, 2, 3, and 4 which wagon is standing. We therefore can estimate where the position or the XY coordinates are in the warehouse, but it's not that sure if it's really at this position, because it's possible that the train push it too far into the warehouse or is at the southern region. At this point, we also are able to give some start of the loading and estimating loading time, and also we are trying to give the workers some instructions when they have to push the wagon covers and when to do that. The crane operator has to compensate the wrong coordinates, so we also have to give him the numbering of the wagons, but he maybe gets some better first position at this point than he has now, because now he is counting the wagons, and therefore he knows where to put the coils. Also here we have to do a full photo documentation, and this is in the next step also one of our goals to do this photo documentation fully automatic, and also to get the covering of the wagons and also the exact positions of the wagons via scanner, and therefore know the exact position in the warehouse. Also, the estimated loading time will be calculated, and also the instructions to the workers how to rearrange the covers of the wagons. Because this is a mainly manual process, so therefore we have no opportunity to do that in an automatic way. The last slide of the digitalization strategies is that we want to operate the crane remotely. So therefore we have to do some legal improvements that we are allowed to do that. Both cranes should not be operated manual anymore. So we want to switch from 100% manual movement to up to 80% automatically. We are also willed to create a digital twin of the cranes to assure that we are able to know what the crane is actually doing, that we are able to give the Josef Ressel Zentrum the data they need. Also some dynamic issues we have to handle: the incoming trucks, the wagon cover movements, the crane failures, and some other effects that maybe a wagon is defect or a truck that was incoming has some uncovering issues. Therefore, we have some major problems that we have to consider and to handle. To see how such a project plan could work is we got a timeline here. So in the year 2020, we started the automatic assignment of transport tasks. We also started the integration of the optimization in our software environment, and also we started the crane automation. In 2021, we we want to start and finish the infrastructure issues. This includes the fans, the doors, and all this stuff. We also want to finish the integration of the optimization in our environment and to continually improve the optimization. And we also want to finish the crane automation and the automatic assignment of transport tasks. What we want to start at this point is that we can remotely operate the crane and also the digital vehicle detection. And these two tasks should be finished in 2022. So this is only an overview. So we consider about 3 years to handle this project in real life. So thanks for your attention, and if there are any questions, then you are.
Thank you, Karl, for this very good talk. And it seems like an impressive task that you have to face automating this whole warehouse facility. Are there any questions from the audience? Please, again, use raise hand if you have a question, or if you cannot use raise hands, please just unmute your microphone. Yes, Victoria has a question.
Thank you, Andreas. Karl, thank you for this interesting talk. You talked about, so in general, about change management from a very generic perspective. So what do you personally think, or how do you feel about this project? What is the most challenging part? Is it the dynamic part, the optimization or simulation part, or is it perhaps something different, like more human resource related? What do you?
Yeah, we have several problems. We have to the crane operators. They have to do that for us to automate this entire cranes. This is a very challenging one because normally they know that they are losing, or some of them may losing their crane operating positions, but we also say them that we have another workplaces left that they have no job issues in our company, but this is one fact. Another one is the data and also the integration of the data to the Josef Ressel Zentrum, because we have to generate the data, we have to give viable data to the Josef Ressel Zentrum that we can assure that we get good results. So there are several such problems that we have to handle.
Thank you.
Thanks for the question.
Are there further questions from the audience? Okay. So then, because we are already a bit late and behind our schedule and we don't want to delay too much, I want to move on to our final speaker, Gerald Fehringer from LISEC, who is talking about challenges and solutions for optimization in the glass producing industry. Please, Gerald, the stage is yours.
Thank you for introducing me. A warm welcome also from my side. And I will talk about the challenges and solutions for optimizations in the flat glass producing industry. My name is Gerald Fehringer and I'm working for a company called LISEC. LISEC is situated in Lower Austria, and LISEC is more or less one of the main suppliers for machinery and even software for the flat glass industry. And as such, I would like to introduce you a little bit into what are the glass products that our machines are capable to do, and what is the production flow, so that you are then prepared for the challenges that I would like to talk about in my main part of the talk. So let's quickly start into the glass products. It is important to note that we have a lot size of 1. That means more or less each and every piece that gets produced is unique. especially if we talk about IGU production for windows and doors. Why is this? Reason is that these orders and items get ordered with a lot of different geometries, means a lot of different sizes, not only rectangular, but also any non-rectangular shapes like you see on the right-hand side. And these products are built from many different materials. There's a variety of a lot of materials that are involved in the buildup. Foremost, of course, the glass as a raw material, which is available in different thicknesses, available in different colors, bluish or greenish, for example, and the glass may carry coatings on at least one of the surfaces. This is important to then in the end have certain physical properties for the final product like IG or laminated units. And what also needs to be highlighted is that the suppliers for the raw material, they deliver the glass in very large stock plates, which is more or less a result of the production flow that happens in such glass factories. Mainly the glass products are divided into three categories. We have single glass units, which is more or less a single glass sheet, and this can be of different materials, like explained, but there is also a lot of sometimes even complex processings that get applied to these glass sheets. The second category is the IGU, which is insulated glass unit, which is very well known, I think, from windows and doors, or if you look at the right-hand side for building facades. These IGUs are built from different glass materials, different spacers, sealants and gas fillings, so there is a lot of combinations possible. And then we have the third category, which is the laminated glass units, which is again more an assembly of multiple glass layers, and in between the glass layers you have foils. And this is a material you very well know maybe from cars. So each front window of a car is made of a laminated glass unit, or on the right-hand side I have put the picture of a staircase where this material is also being used, or bulletproof glass, for example, is also this kind of product. For my talk, I would more like to concentrate on IGU at this point, the insulating glass units. As we can see, we have different buildups that can be 2, 3, 4, 5 pane glass units, where the 2 and 3 pane glass units are more or less used for windows, the 4 and 5 pane units more for doors because of the extra, let's say, stability and security extension that comes with the additional layers. If you look at the cross section on the right-hand side, where we have a sketch for a 3 pane unit, you will see that we have 3 glasses. These glasses are separated by spacers, where the spacer can be either rigid material or thermoplastic material. Rigid material would be, for example, aluminum or steel. And then between the glasses and the spacer or the frame material, we have first of all the primary seal, and then the secondary seal, which is more or less at the outside, just around the whole unit, more or less. And this sealant should make sure that the gas that might have been filled in does not escape, and we preserve, let's say, the physical properties of the final element. As we can also see, there is coatings, or there can be coatings on one of the glass surfaces, and these coatings also serve certain properties, like or use cases like solar control. Means, okay, we want to block UV radiation, or the low E is more for preserving heat and avoid emissivity towards the outside. So once again, we have a lot of different glass, spacer, sealant, and gas materials. This brings in the variety plus the different sizes. So this is the important point where we have lot size 1 production, and this is one of the key points also finally for the production workflow, because if glass breaks, then that material is gone, of course, and we have to restart the full production process right from the beginning. Short introduction to the production workflow, just to understand a little bit the processes. I've put here a sample plant layout of a still rather simple production, trying to explain the most important processing areas. So like I said, we have stock plates coming from the glass suppliers. Those get stored in a stock where we then put forward these stock plates onto the cutting section. The cutting section then breaks down more or less the smaller pieces, and when we end up with the order item sizes, these glasses then get moved into a buffer, and this buffer serves especially also the purpose of sorting, because then at the end we have to unload single glass pieces onto this long IG line, where in the process of building the IG element, those single glasses get assembled and sealed, and finally the ready-made IG unit then gets moved into the dispatch area. So this was just a quick overview of how the process here is. And now let's move into the challenges that arise from this setup. Mainly, I will start at the very end of the production, which is the dispatch, because the dispatch then implies a lot of restrictions to the production process that is ahead of the dispatch area. Looking at the dispatch, we need to know that the transport more or less, or to a large percentage, happens on racks. These racks get loaded onto trucks, and the trucks then deliver the goods to the customers, of course. And our customers, of course, are interested in minimizing the transport cost, which means we have to minimize the number of racks to be used, which in turn means we should maximize the load on a single rack, of course. Yeah? And while we do this loading of racks, we have to, let's say, deal with a lot of restrictions. And the foremost restriction here is to preserve a stacking sequence. So if we look at the right-hand side, I have the bird view and the front view of a rack, where you see, okay, the operator here should load a new element in green color named B, and this is only possible to be put in front of a stack, or we start a new stack, or we even start a new rack. Reason for this being more or less the golden rule in the glass production, that we should reduce the number of glass handlings as much as possible. That means every movement, every restacking should be avoided, because that introduces an additional risk of breakage or scratching the glass or whatever. So we would have to restart the process from the very beginning, and this needs to be avoided. So this is the loading sequence, and also the unloading sequence then determines more or less this restriction. And why do we have this stacking sequence, or why would we need to follow a certain stacking sequence? This is because the IG units mainly move or go to two main, let's say, end customers. The one being the building industry, where they want to use IG units for facades. And of course, for their work, it is ideal if they can unload the elements one by one from the rack and directly mount it into the facades. So when they order such IG elements from our customers, then they also provide instructions of what is the expected delivery sequence. And the second group of end customers is the window producers, because the window producers themselves, they have already a predefined sequence for the window production. And then, of course, it's also their interest that they are able to unload the ready-made IG units in this predefined sequence already, because also at their end, they have the problem, if there is need to restack the items, then this introduces additional risk for breakages. Yeah, and besides the stacking, we have other rules to accomplish, like the maximum overlap. That means if we put an element in front of another one, then the overlap between those elements should be or should not exceed a certain maximum, because otherwise some forces could make the elements break again. We have different sizes of racks with different weight limits, which we have to fulfill. If there are two sides, then we should have a load balancing so that the forklift driver doesn't run into troubles when he is then loading or transporting these racks. And customers very often also ask for grouping the products, means like a window producer, and a window producer might have two production lines, A and B. And if they order elements for a particular day, then they order it for A plus B. And of course, they would like to have the elements separated already to be able to feed their production lines. For this problem, the stacking problem or the delivery problem, we have an existing solution implemented ourselves, which is a delivery rack optimization plus an editor delivered alongside with it that still allows to, let's say, manually improve the result of the automatic algorithm. And this is how many customers are working in the flat glass industry. When we go a step back, then that step back means we look at IGU assembly. This is the process that happens before we can deliver. And if we look at such an IG line, we see, or we already grasped, that it is a long line where we have a starting point on the left-hand side, in this case, where we load the single glass pieces. Those get moved through a washer first, then they pass a spacer application where some of these glasses then get a spacer applied, and then the glasses move into the press, where more or less the glass gets stacked onto each other, and the spacer makes sure that we keep or preserve a distance between the glasses, and the press then also makes sure that together with the primary sealing, the element sticks together. Then it gets moved on to the sealing robot, where gas filling might happen, and the secondary sealing all around is happening, and then afterwards the unit is taken off, and ideally we take it off and already place it directly onto the delivery rack, so that for production, or not for production, for the delivery, there is no additional handling required, and they can directly load then the delivery racks onto the trucks. So here again we have the dependency on the delivery rack sequence. What does that mean? In the end, we have a FIFO buffer here, means whatever glasses we load at the inlet section of the IG line is the first unit that is taken off at the end of the IG line, of course. Besides this principle of following, let's say, the production sequence for the final delivery racks, there is also, let's say, IG element internal. We also have to make sure that the sequence of the glasses loaded onto the IG lines is done in a way that finally the buildup looks like the ordered buildup, of course. Means if we have, or if we recall the cross section here of the IG element, we have three glasses, and let's say the rightmost glass should be the first glass, then the middle glass the second glass, and the left hand glass the last glass to be loaded, because once these glasses are on the IG line, there is almost no way to change the sequence of those glasses, and while the stacking happens in the press, this the sequence of the glasses is predefined with the loading already. And like this picture also illustrates, we have the coating, which is required in certain positions to make sure that the element then fulfills certain physical properties. And we also have to make sure that these coatings get, let's say, assembled correctly, especially taking care of the fact that this coating is sensible against, let's say, scratches if we run this coated surface against the board of the machine, of course. Yeah? So in this case, we have to make sure that we either run the glass with the coating facing away from the board, from the backboard, which means we also need to make a reversed or mirrored build. We have to make sure to do this, and this already has to be considered while we load the IG line. What are solutions to make sure that we can load in a sorted or in a sequenced manner? Of course, there is physical solutions available, like on the right-hand side larger picture, where we see a buffer system of ours, which means there is physical boxes with slots divided by strings, and each slot more or less can hold 1 or 2 pieces of glass. And let's say in the simplest way, we load these boxes from one side and unload these boxes from the other side. That buffer more or less serves a certain buffer functionality, means the single glasses that may arrive from different areas of the production get collected there, and once all the glasses are available, at least for a single IG unit, but ideally for, let's say, at least a complete rack or a complete batch, then we start the unloading towards the IG line. This is quite an expensive, let's say, machinery part, so maybe only 5 to 10% of our customers really make use of such a physical buffer. The other possibility for a solution for the sorted loading is using harp cars, like we see in the bottom picture on the left-hand side, which are more or less cars also having strings dividing the space into slots. And while we unload towards the IG line, we either work from right to left or left to right, or at least the operator wants to work this way because this simplifies his work. He doesn't have to think about, okay, what should be the next piece of glass to be unslotted and loaded onto the IG line. So anyways, he more or less works in a sorted manner here, but the advantage is that at least the loading of the harp car can happen in an arbitrary manner compared to if we look at, and this is the third mechanism, using internal racks. Even the harp cars are rather expensive compared to racks, and this is why, let's say, at least more than 50% of our customers still make use of racks, of internal racks, to move or to store glass inside of the production, not only for the delivery, but also for the internal storage, for the internal movement of the glass products between machines. And here, of course, ideally, when we cut the glass, and the glass cutting happens per glass type, of course, then after cutting, the glass needs to be stacked on the racks. And ideally, when then later on this rack gets moved to the IG line, again, the operator would like to just simply unload one piece of glass after the other from this rack without having to restack. So again, already at the cutting process, the final production sequence and the final delivery sequence more or less influences the way of cutting. So here we decide, or here we have a solution that says, okay, we make use of internal racks. We try to fill these racks per glass type, and we make sure that we build stacks that later on can be easily unloaded at the inlet of the IG line. So this brings me to let's say, the starting point of the production, which is the cutting. Cutting might be a little bit misleading term, at least in the glass industry, because you cannot compare the cutting here with cutting a piece of paper or a piece of cloth, because you cannot apply a scissor to cut out any arbitrary shape here. Cutting in the glass industry means we use a diamond wheel, and the diamond wheel scribes the surface of the glass, and then by applying a force at the bottom or directly under this scribe, luckily the glass breaks, and it luckily breaks along the scribe, at least as long as we, let's say, fulfill some of the breakout rules. One of these breakout rules, for example, is that the distance between two scribes should at least be, let's say, 20 millimeters. The distance depends on the glass thickness. So if such scribes would be placed, let's say, closer than 20 millimeters, then while breaking the glass along one of the scribes, the break could escape the scribe and run into the other scribe, and then unexpectedly run maybe into the finally useful glass area, and then introducing remakes and breakage, of course, which should be avoided. In the end, it means we need a 2D optimizer for the glass, of course, with the goal of minimizing the waste and minimizing the material cost. And as expected, we want the breakout sequence of the smaller pieces to happen already in a way that we can then stack the glass onto the internal racks, again prepared for the IG line and again prepared for the delivery. So this is, in essence, why I started with the delivery area as an explanation why this influences the whole production flow. There would be other areas where we have challenges and where we also provide solutions partially, but okay, coming back to, sorry, I missed this slide. We have, of course, solutions for the glass cutting, for the 2D optimizer. On the left-hand side, you see such a result where, yeah, I mean, the 2D cutting optimization always has to make sure that we have a scribe that is more or less dividing the large piece into two smaller pieces, and then the two smaller pieces can again be divided into another two smaller pieces, and so on, till we finally end up with the desired order item geometries and sizes. What we also have is a so-called true shape optimizer. That means in the glass industry, everything that is rectangular can be treated rather easily. It can be cut rather easily, broken out rather easily. Everything that is not rectangular adds an extra burden of manual breaking and additional, let's say, trim cuts required to be able to break such a shape. And we have implemented an algorithm where, let's say, years ago, all such shapes had to be cut out from, let's say, a rectangle, and inside of that rectangle, we always had only sitting one of the good shapes for the order items, and our algorithm is capable of nesting arbitrary shapes into, let's say, rather optimal rectangles to reduce the wastage, like you see on the right-hand side. Yeah. So this is where we have, let's say, established quite a lot of, I call it, local area optimizations. Means at the cutting we have a 2D optimizer, and for the delivery we have a delivery rack optimization. For the buffer we can, let's say, optimize the utilization, how we occupy the slots for the buffer. But despite having these local optimizations, this does not mean that we have an optimum solution for the global production. And this is, of course, where we want to head into smart production, which is anyway something where a lot of industries are heading for. The problems we currently still don't cover are that we still have a lot of manual decisions to be made by humans. Means we have batch planners, we have operators that decide what is the size of batches, what are the characteristics of batches, what products do we group together, what should be the next optimization to be cut, for example, what should be the next batch to be assembled at the IG line, and so on and so on. Plus, we have that extra burden of remakes. Like I explained, if glass breaks, then the material is of course gone, and this requires a restart right from the beginning. This might cause problems at the 2D optimizer, for example, because we might have low volume of material available to really optimize the glass usage, or this might disturb the production runs because the remakes then arrive with different characteristics, materials, whatever, which then causes machines to run into preparation times and causes the cycle times to be destroyed. So here, with the help or being part of the adaptOp Josef Ressel Center, our goal is, of course, to establish solutions in this direction of smart production together with the research group headed by Stefan Wagner, and this is where we hope that in the coming years we can provide added values to our software stack and to our customers. With this, I'm ending my talk. Thanks for your attention, and I hope you don't mind that I exceeded the time limit a little bit.
No problem. Thank you very much, Gerald Fehringer. I think we continued with the delay from the start, but nevertheless, I want to thank you for this very, very interesting insight into the challenges of the glass producing industry. Again, I would want to give the audience a chance to ask a question. I think there are no more sessions today, if I'm not mistaken. So, is there some question? In the audience, use the raise hand feature if you have a question. Stefan.
Yeah, yes, please. Thank you, Mr. Fehringer, for your insights into glass production. And I think this is very, very interesting because in your case, you are a machine manufacturer. Yeah, so you are thinking about process optimization and what you can do, in fact, for your customers, for the companies who use your machines. And I think this is an interesting situation compared to other presentations that we heard in this conference, where the companies who are directly producing things are explaining how they think about Industry 4.0 and smart manufacturing. So my question would be, what is your feeling regarding your customers and regarding the awareness of technologies that we discuss here for glass manufacturing companies who use your machines? Is it that you feel that there is a strong pressure from your customers that they need technology and optimization approaches that we discuss now, or do you think that it's rather your role as a machine manufacturer to push technologies and solutions towards the companies using your machines?
Yeah, in fact, it happens both sides, because we, let's say, gather ideas coming from different customers and try to find, let's say, a common sense solution for the customers. That's one side. On the other hand, for example, if we talk about customers in Australia or New Zealand and so on, they have a very, let's say, expensive staff structure, and they, of course, intend to automate as much as possible. And from their end, we receive really a lot of pressure to improve the systems, to make, to get away from, let's say, operators making decisions in the system, to simplify the work, because what we often see that if we start up such a factory and they hire the staff, then there is a learning curve, and that learning curve is sometimes quite slow. And to be able to run this factory, then let's say in an acceptable way of what they finally try to get as output from the factory, this takes quite a lot of time till they are at this level. And if we can offer, let's say, software solutions to this to speed up this process, then of course this would be helpful. And also, let's say the staff is of normally low degree education, let's say this way. So simplifying their operations in the plant is one of the main goals also. And still preserving, let's say, the quality and the speed of the factory. This is the interest the customers have that we want to serve, of course, and this is where we put hope in our project.
Thank you.
Thank you very much. And any further questions that we have here? I very much also enjoyed this picture that you have drawn regarding these local optimizations, and that puts together kind of the production, the whole production system, and how we are still missing the global picture by doing all these local optimizations. So that is that reminds me of the ideas that we had in this Hoppel project that we finished in 2018, and I think continuing there, and especially when we have these more dynamic models in place and these interactions, and then revisiting probably some of the research that we started with Hoppel is something that I already see as a future goal past the Josef Ressel Center to combine these different aspects. It's a very good outlook, I think.
Looking forward to this, yeah.
Okay, so thank you very much again for your talk. Thanks all to the speakers for this talks, and the audience for having stayed with us here. I think we had two very good sessions. Before concluding this session, I want to also advertise our session tomorrow morning on integrated logistics planning, which is chaired by my colleague Victoria Hauder. And there are two sessions. One is on a scientific track, and one is again a special sessions with keynotes from Risk Software, if I remember correctly, and the University of Klagenfurt, and also from University of Linz. So please join us in the sessions on integrated logistics. I thank you very much for having joined us here with dynamic optimization. I think it's a very hot topic. We will definitely have a long-running research program, and I hope to be able to participate and contribute to this conference in the future.